Tonight we were going to talk about the crisis unfolding in cosmology right now. For decades we thought we understood the scale of our universe. We had measurements, calculations, models that told us how big everything was, how far galaxies stretched, how much time the universe needed to build the structures we see today. And then Webb looked deeper than any telescope before it. What it saw wasn't just unexpected, it was impossible. Galaxies that shouldn't exist. Appearing in places they had no right to be. Structures forming billions of years too early. A universe that wasn't just bigger than we thought, but fundamentally different from what our best theories predicted. And by the end of tonight, you're going to understand why everything we thought we knew about the true scale of the universe was built on incomplete data, and how Webb's discoveries are forcing us to rewrite the cosmic story from the very beginning. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. For decades we had it all figured out. The universe was 13.8 billion years old, born in the Big Bang. After that initial explosion, space expanded and cooled. About 380,000 years later, the universe became transparent. Light could finally travel freely through space, but stars didn't form immediately. There was a period astronomers call the Cosmic Dark Ages, lasting from about 380,000 years to about 100 to 200 million years after the Big Bang. During this time, the universe was dark, filled with hydrogen and helium gas, but no stars to light it up. Eventually, gravity pulled that gas together. The first stars ignited around 100 to 200 million years after the Big Bang. These population 3 stars, as we call them, were massive, pure hydrogen and helium with no heavier elements. They burned hot and died fast, leaving only a few million years before exploding as supernovae. Those explosions scattered the first heavy elements across space, carbon, oxygen, iron, and these elements would be incorporated into the next generation of stars. This process took time, lots of time. Our models predicted that the first small galaxies wouldn't form until about 300 to 500 million years after the Big Bang, and these early galaxies would be primitive. Small collections of stars, maybe a few million to a few tens of millions, irregular in shape without organized structure. No spiral arms, no clear centers, just chaotic clumps of stars held together by gravity. Over the next few these small galaxies would merge. 2 small galaxies colliding would form a slightly larger one. That larger galaxy would collide with others, growing bigger each time. It was cosmic construction, building cathedrals from individual bricks over billions of years. By the time the universe was about 1 billion years old, we expected to see galaxies containing maybe a 100 million to a few hundred million stars. Still relatively small, still irregular, but starting to show hints of structure. By 2 billion years, galaxies might reach 1 billion stars. By 3 billion years, organized structures like spiral arms might begin to form. The Milky Way, our home galaxy with its 400 billion stars and its beautiful spiral structure, took about 13 billion years to form. That timeline made sense. It matched what we knew about gravity, about how gas collapses to form stars, about how galaxies merge and grow. The math worked, the physics worked. Hubble Space Telescope observations seemed to confirm this timeline. When Hubble looked at galaxies about 10 billion light-years away, seeing them as they were 10 billion years ago, those galaxies looked more primitive than nearby ones. When Hubble pushed to its limits, imaging galaxies about 12 to 13 billion light-years away, seeing them as they were just a few hundred million years after the Big Bang, those galaxies were small and faint, exactly as predicted. We also knew how many galaxies should exist at different distances close to us. In the recent universe, galaxies are common. Space is full of them. But as you look farther back in time, galaxy density should decrease. Fewer galaxies exist in the young universe because they haven't had time to form yet. Our calculations suggested that when the universe was 500 million years old, there might be 10 to 20% as many galaxies per unit volume as exist today. When the universe was 300 million years old, maybe only 1 to 5% of today's density. This made sense because galaxies form gradually. You start with very few, and the number increases over time as more gas collapses and more structures form. We estimated the observable universe contained about 200 billion to 2 trillion galaxies total. That's already an incomprehensible number, but it was a number we trusted based on decades of observations and solid theoretical foundations. The observable universe itself was calculated to be about 93 billion light-years in diameter. That's not the same as the age of the universe times 2. The universe is 13.8 billion years old. So you might think light could only have travelled 13.8 billion light-years, but space has been expanding all this time. Objects that emitted light 13.8 billion years ago are now much farther away because space itself stretched while the light was travelling. When we account for that expansion, the most distant objects we can see are now about 46.5 billion light-years away. Double that and you get the 93 billion light-year diameter. Everything we could observe fit inside that sphere. And within that sphere, structure was organised in a specific way. At the smallest scales, you have individual galaxies. Galaxies group together into galaxy clusters containing dozens to thousands of galaxies. Clusters group into superclusters containing tens of thousands of galaxies, and superclusters form part of the cosmic web, a structure of filaments and voids that spans the entire observable universe. This web took billions of years to form. Gravity pulled matter together along filaments, creating the threads of the web. Between the filaments are vast voids, regions nearly empty of galaxies. Our models predicted this structure started forming when the universe was at least a few hundred million years old, with the cosmic web taking billions of years to become as defined as what we see today. Everything fit together. The timeline, the structure, the galaxy counts, the evolution from simple to complex. We had a complete picture of cosmic history from the Big Bang to today. It was elegant, it was testable, it was confirmed by multiple independent observations. We called this the Lambda Cold Dark Matter Model, or Lambda CDM for short. Lambda represents dark energy, the mysterious force causing the universe's expansion to accelerate. Cold dark matter represents the invisible matter that makes up most of the universe's mass, providing the gravitational scaffolding for galaxies to form. This model had been refined over decades. It matched the cosmic microwave background, the afterglow of the Big Bang. It matched the large-scale structure we observe. It matched the expansion rate measurements. It matched galaxy evolution as Hubble observed it. There were a few minor puzzles, things that didn't quite fit perfectly. The Hubble tension, where different methods of measuring the expansion rate gave slightly different answers. Some observations suggesting galaxies might have slightly more organized structure than expected at certain epochs, but these were seen as measurement uncertainties, small discrepancies that would be resolved with better data. Nobody expected the model to be fundamentally wrong. Nobody expected James Webb to reveal that almost everything about our timeline was off. Then the James Webb Space Telescope launched on December 25, 2021. The telescope music was designed to see what Hubble couldn't. While Hubble observed primarily in visible light, Webb observes in infrared. This difference is crucial for studying the early universe. Light from the most distant objects is redshifted, stretched to longer wavelengths by cosmic expansion. Light that starts as visible or ultraviolet gets stretched into infrared by the time it reaches us. The farther away something is, the more its light is redshifted. Webb's infrared vision allows it to see objects so distant that their light has been stretched completely out of visible wavelengths. Objects Hubble could barely detect or couldn't see at all. Webb also has a much larger mirror than Hubble. Webb's mirror is 21.3 feet across, with a collecting area about 6.25 times larger than Hubble's. More mirror means more light collected, which means fainter objects become visible. Combined with its infrared capability, Webb can see galaxies forming in the first few 100 million years after the Big Bang with unprecedented clarity. This is what it was built for: to look at the universe's first light, to see how the first galaxies formed, to test our models of cosmic dawn. On July 12, 2022, the first deep field image from Webb was released. The target was a galaxy cluster called SMAX 0723. The image showed the cluster in stunning detail, but even more impressive was what lay beyond it. Thousands of distant galaxies stretching across cosmic time, each one appearing as a small smudge or arc of light. Astronomers immediately began analysing these galaxies, measuring their distances through spectroscopy, determining their properties, comparing them to predictions, and almost immediately something was wrong. The galaxies in the deepest background, the ones that should be the most primitive, weren't primitive at all. They had structure. They had mass. They looked organised. One of the first anomalies identified was a galaxy designated Glass Z13. Spectroscopic analysis confirmed it existed just 300 million years after the Big Bang. That was already pushing the boundaries of what models predicted, but possible within the Lambda CDM framework. But this galaxy contained approximately 1 billion stars, 1 billion at 300 million years after the Big Bang. For context, so forming a billion stars requires an enormous amount of gas to collapse, fragment, and ignite. Even under ideal conditions with perfectly efficient star formation, this should take at least 500 million to 1 billion years. Glass Z13 did it in 300 million. The timeline didn't work. Then came Sears 933, another early galaxy from WEE's Cosmic Evolution Early Release Science Survey. This galaxy also existed around 300 million years after the Big Bang. It was massive, containing hundreds of millions of stars, and showed signs of organised structure. Not a chaotic clump, but something with shape, with internal organisation. Then JWST 30 discovered it as part of the JWST Advanced Deep Extragalactic Survey. This galaxy existed about 330 million years after the Big Bang. Again, massive, again organised, again containing far more stars than should be possible in that time frame. These weren't outliers, they were everywhere Webb looked. The JADE survey alone found dozens of galaxies in the first 500 million years of cosmic history that were too massive, too structured, too mature for their age. But the real shock came with JADE's GST 140. Initial analysis suggested this galaxy existed just 290 million years after the Big Bang, less than 300 million years, and it contained something that absolutely shouldn't exist at that point in cosmic history, a supermassive black hole. The black hole at this galaxy's pista had a mass estimated at several million times the mass of our Sun. Black holes that massive shouldn't exist in the early universe. Here's why. Black holes form when massive stars die and collapse. But a stellar mass black hole formed from a single star might be 10 to 100 times the mass of the Sun. To grow from stellar mass to supermassive millions or billions of solar masses, the black hole needs to feed. It needs to accrete matter from its surroundings. But there's a limit to how fast a black hole can grow. As matter falls toward a black hole, it heats up and emits radiation. That radiation creates pressure that pushes against in falling matter. This is called the Eddington limit, and it sets a maximum rate at which a black hole can accrete mass. Even feeding at the Eddington limit constantly, it takes at least hundreds of millions of years to grow a black hole from stellar mass to millions of solar masses. Jade's GSZ 140 had less than 300 million years, and that assumes the black hole formed immediately at the start of that period, which it couldn't have because you need the stars to form first, live their lives, and then collapse. The timeline was impossible. Unless something about our understanding of black hole growth was wrong. Unless black holes in the early universe could somehow bypass the Eddington limit and grow much faster than physics should allow. Or unless these black holes didn't form from collapsing stars at all, but through some exotic process we don't understand. Either way, the observations didn't match the theory. As Webb continued observing, the problem only got worse. The density of galaxies in the early universe was far higher than predicted. When the lambda CDM model predicted the universe at 500 million years old should contain maybe 10 to 20% of today's galaxy density, Webb found something closer to 50 to 70%, 3 to 5 times more galaxies than expected. At 300 million years, where models predicted 1 to 5% of today's density, Webb found 20 to 30%, 5 to 10 times more galaxies than expected. These aren't small discrepancies. These are fundamental mismatches between theory and observation. And it wasn't just the number of galaxies, it was their mass distribution. Surveys found that massive galaxies, ones containing 10 billion stars or more, were surprisingly common in the early universe. According to pre-Webb models, galaxies that massive shouldn't exist until the universe is at least 1 to 2 billion years old. Yet Webb found them at 500 million years. At 700 million years, massive galaxies that had no business existing yet. One study analysing Webb data found galaxies in the early universe that were as massive as the Milky Way. Our galaxy took 13 billion years to accumulate its 400 billion stars. Webb was seeing Milky Way mass galaxies when the universe was less than 1 billion years old. How do you compress 13 billion years of growth into less than 1 billion? The math doesn't work. Even if star formation was perfectly efficient, even if every bit of available gas turned into stars with no waste, you can't form that many stars that fast. Gas clouds can only collapse so quickly. Stars can only form so fast. There are physical limits built into the process. Gravity works at a certain speed. Gas has pressure that resists collapse. Forming stars requires cooling, and cooling takes time. You can't speed it up indefinitely. Yet somehow the early universe was doing exactly that, forming massive galaxies orders of magnitude faster than our models predicted. The structure of these early galaxies was equally surprising. Pre-Webb models predicted that early galaxies would be irregular, chaotic, without organised structure. Spiral arms and galactic disks should take billions of years to form, but Webb found galaxies with disk-like structures at 700 million years. Galaxies with elongated shapes suggesting rotation and angular momentum at 500 million years. Galaxies showing signs of spiral arms at 1 billion years, billions of years earlier than expected. The universe was organised from almost the very beginning, not chaotic and primitive, but structured and sophisticated. Another shocking discovery was the presence of protoclusters in the early universe. Protoclusters are the ancestors of today's massive galaxy clusters. They're regions where dozens of galaxies are forming close together, bound by gravity, destined to merge into a single enormous cluster over cosmic time. Our models predicted protoclusters wouldn't form until the universe was at least 500 million to 1 billion years old. Webb found them at 300 to 400 million years. Not just a few galaxies near each other by chance, but gravitationally bound structures already showing the organisation that will define the cosmic web. This meant large-scale structure was forming far earlier than our models allowed. The cosmic web, that vast network of filaments and voids, wasn't something that gradually emerged over billions of years. Its foundations were being laid in the first few 100 million years. Chemical composition added another layer of confusion. When the universe began, it contained only hydrogen and helium. Everything heavier, what astronomers call metals, had to be created in stars through nuclear fusion. The first generation of stars, population. 3 stars were pure hydrogen and helium. When they died, they enriched the surrounding gas with heavier elements. The second generation incorporated those elements. The third generation incorporated even more. This enrichment process takes time. You need multiple generations of stars living and dying to build up significant metal content. Our models predicted that galaxies in the first few 100 million years would be metal poor, containing mostly hydrogen and helium with only traces of heavier elements. But Webb's spectroscopy showed surprisingly high metal abundances in some early galaxies, metal content that should require multiple stellar generations to produce present when the universe was barely old enough for 1 or 2 generations. This suggested the cycle of star formation and death was happening incredibly fast in the early universe. Stars forming, living their brief lives, exploding, enriching the gas, and that gas forming new stars all in timeframes measured in tens of millions of years rather than hundreds of millions. The pace of chemical evolution was far faster than our models predicted. By late 2022 and into the 2023, as more Webb data accumulated, astronomers began using the term crisis in cosmology. This wasn't hyperbole. The lambda CDM model, our standard model of cosmology, refined over decades and tested against countless observations, was failing to explain Webb's observations, not failing in minor ways, failing fundamentally. The model predicted a certain timeline for galaxy formation. Webb showed that timeline was wrong by factors of 2 to 5. The model predicted certain galaxy densities at different epochs. Webb showed densities 3 to 10 times higher. The model predicted primitive irregular galaxies in the early universe. Webb showed organized, massive, structured galaxies. Every major prediction about the early universe was wrong. Some astronomers initially questioned whether the observations themselves might be wrong. Maybe the redshift measurements were incorrect. Maybe these galaxies weren't as distant as they appeared, but Webb spectroscopy is extremely precise. Redshift measurements are based on identifying specific spectral lines from elements like hydrogen and oxygen and measuring how much those lines have been shifted to longer wavelengths. It's one of the most reliable measurements in astronomy. Multiple independent teams analysed the data and confirmed the redshifts. The galaxies really were that distant. They really were forming when the universe was only a few 100 million years old. Others suggested maybe star formation in the early universe was just more efficient than we thought. Maybe conditions back then allowed gas to convert into stars at higher rates. But even pushing efficiency to theoretical maximums where every available bit of gas becomes a star with zero waste, the numbers barely improve. You still can't form billion-star galaxies in 300 million years. The timeline is too short. Some researchers propose that maybe the first stars were more massive than we assumed. If population 3 stars were typically 100 to 300 times the mass of the Sun, as some models suggest, they would live very fast, die very fast, and enrich the cosmos with heavy elements, much more quickly than normal stars. This could speed up chemical evolution, but it doesn't solve the mass problem. Even if enrichment happens faster, you still need time for gas to collapse into stars. Multiple rounds of collapse and formation take time. No matter how massive individual stars are, the Hubble tension, already a puzzle before Webb, became worse. The Hubble tension refers to a discrepancy in measurements of the universe's expansion rate called the Hubble constant. When you measure the Hubble constant using the cosmic microwave background, the afterglow of the Big Bang, you get a value around 42 meters per second per megapark. When you measure it using observations of nearby galaxies and supernovae, you get around 45 meters per second per megapark. These numbers disagree by about 9%, far more than measurement uncertainties can explain. Before Webb, astronomers hoped better observations might resolve this tension by refining one measurement or the other. Instead, Webb's precise distance measurements of faraway galaxies have confirmed that the tension is real. The expansion rate seems to be different depending on where and when you measure it. If the expansion rate isn't constant, if it varied over cosmic history in ways our models don't account for, then all our calculations of distances and ages become uncertain. Maybe the universe is older than 13.88 billion years. Maybe it expanded faster in early epochs. If the universe is older, that gives more time for structure to form, potentially explaining some of Webb's early galaxy observations. But changing the age creates other problems. The cosmic microwave background gives us a very precise age based on well-understood physics. To change that age, you have to change the physics which affects everything else we think we know about the universe. Dark matter distribution also became problematic. Webb's gravitational lensing observations, where massive objects bend light from more distant sources, allow us to map how dark matter is distributed. These maps show dark matter clumped in ways that don't quite match simulations. In some regions, it's more concentrated than predicted. In others, it's more spread out. The discrepancies aren't huge, but they're consistent. Something about how dark matter behaves or how it clumps together over time doesn't match our models. If dark matter clumps faster, that could help explain rapid galaxy formation. Denser dark matter halos provide stronger gravitational wells, pulling in normal matter more quickly. But this would require dark matter to interact with itself, or with normal matter in ways we haven't detected. It would require new physics. Some cosmologists propose modifications to the lambda CDM model. Maybe dark energy, the mysterious force accelerating cosmic expansion, was stronger in the early universe that could affect how structure forms. Maybe dark matter has properties we don't understand, like weak self-interactions that change its distribution. Maybe the initial conditions right after the Big Bang were different from what the cosmic microwave background suggests. Tiny variations in those initial conditions could cascade into large differences in structure formation. But every proposed modification created new problems. Change one parameter to fix early galaxy masses and you break the fit to large-scale structure observations. Adjust another parameter to match galaxy densities and you mess up predictions for the cosmic microwave background. The model is interconnected. Change one piece and everything shifts. Finding a modification that explains Webb's observations without breaking everything else has proven extremely difficult. Some researchers began exploring more radical ideas. What if our understanding of gravity is wrong on cosmic scales? What if general relativity, Einstein's theory that's passed every test for over a century, breaks down in the extreme conditions of the early universe? Modified gravity theories have been proposed before, mostly to explain dark matter without invoking invisible particles. These theories suggest that gravity behaves differently at very large distances or very low accelerations. If gravity was stronger in the early universe, that could help structure form faster. But modified gravity theories have their own problems, and most have been ruled out by observations. The few that remain are highly speculative and would require overthrowing one of the most successful theories in all of physics. Other researchers looked at exotic possibilities. What if there was a period of rapid structure formation triggered by some unknown process in the early universe? What if primordial black holes formed in the Big Bang rather than from collapsing stars, seeded early galaxies? What if dark matter decayed or interacted in the early universe in ways it doesn't now, temporarily boosting structure formation? These ideas are speculative, hard to test, and would require physics beyond our current understanding. But the observations demand explanation. You can't just ignore data that contradicts your model. Science advances by updating theories when new observations don't fit. That's what's happening now. Cosmology is in a period of upheaval, trying to reconcile decades of solid theory with observations that don't match. It's uncomfortable for many astronomers who've spent careers working within the Lambda CDM framework. But it's also exciting because when your theories fail to match reality, it means there's something new to discover. Some fundamental aspect of how the universe works that we haven't understood yet. So what does all this mean for the true scale of the universe? If Webb's observations are forcing us to rethink galaxy formation timelines, they're also forcing us to rethink how much structure exists in the cosmos. The observable universe is still 93 billion light-years across. That measurement hasn't changed. It's based on the age of the universe and the speed of light, both of which are well established. But what fills that volume is radically different from what we calculated before Webb. We estimated 200 billion to 2 trillion galaxies in the observable universe. Those estimates were based on galaxy surveys covering small patches of sky, then extrapolating to the full volume. The extrapolations assumed galaxy density decreased as you looked back in time. Fewer galaxies in the young universe, more in the mature universe. But Webb shows that assumption was wrong. Galaxy density in the early universe is much higher than predicted. If we recalculate based on Webb's observations, the total number of galaxies could be significantly higher. Some estimates now push toward 5 to 10 trillion galaxies. That's not just a revision. That's a fundamental recalculation of how much organized structure exists in the cosmos. Each galaxy contains billions to trillions of stars. Each star potentially hosts planets. The sheer amount of matter organized into structures is staggeringly larger than we thought. But it's not just quantity, it's the nature of that structure. We thought the early universe was simple and gradually became complex. We thought structure emerged slowly over billions of years. Webb is showing the universe was complex from almost the beginning. Organized structure appeared in the first few 100 million years. The cosmic web started forming immediately. Massive galaxies assembled in timeframes we thought impossible. This changes our understanding of how the universe works at the most fundamental level. It suggests the processes that create structure are far more powerful, far more efficient than we understood. Gravity works faster, gas collapses quicker, stars form more readily. The universe has a natural tendency toward organization that's stronger than our models predicted. And if the observable universe is more densely packed with structure, what about the universe beyond what we can see? The observable universe is limited by the speed of light in the age of the universe. Beyond that horizon, there's more universe. We can't see it directly, but we can infer its existence. Most cosmological models suggest the total universe is much larger than the observable portion. Some estimates say it's at least 250 times larger in radius. Others suggest it could be exponentially larger if cosmic inflation, the rapid expansion in the first fraction of a second after the Big Bang, extended the universe beyond what we calculated. If the universe beyond our horizon follows the same patterns Webb is revealing, if it's populated with the same density of galaxies forming at the same accelerated pace, then the total amount of structure in reality is almost incomprehensibly larger than we thought. Take the observable universe's trillion plus galaxies and multiply by whatever factor the total universe is larger. 250 times larger in radius means about 15 million times larger in volume. 15 million times a trillion galaxies. The numbers stop making sense at that scale, but the implication is clear.